This is question 10, exercise 2.8. Show that y equals 1 over x minus 2 has no stationary points, and then find the maximum and minimum values of the curve for minus 3 less than or equal to x less than or equal to 3. Right, first of all, let's show that it has no stationary points. Of course, you're going to find the first derivative, y dash, or dy dx, and you're going to let that equal 0 for stationary points. Okay, so let's do that. The dy dx, okay, if you rewrite y, it would be y equals x minus 2 to the power of minus 1. Okay, so we just bring the minus 1 down, write down what's inside the brackets, subtract 1 from the power, and differentiate what's in brackets, which is 1, so we don't need to write anything. So the answer will be minus 1 over x minus 2 squared. Okay, now if you let the stationary points, we're going to let dy dx equal to 0. And if we let minus 1 over x minus 2 all squared equal to 0, we can't solve that. Okay? So, no solutions. Alright, so we can't get, there are no stationary points on the curve y equals 1 over x minus 2. Okay, so now, but we can find other things. We can find the y-intercept, so let x equals 0. If we substitute that, we're going to get y equals 1 over 0 minus 2, which is equal to minus a half. So therefore, 0 minus a half is your y-intercept. Alright, now, you can't get an x-intercept because if you try to find the x-intercept, let y equal 0 and you can't get a solution. So no x-intercept. Right. However, there is a vertical asymptote because x cannot equal 2, right? X cannot equal 2 because if it is, that's going to become undefined. And so x equals 2 is a vertical asymptote. Okay, looking for other asymptotes, y cannot equal to 0 either because you've got 1 over x minus 2, and that number can never be 0 no matter what x value you put in there. So y cannot equal 0, which means that y equals 0, which is our x-axis, is the horizontal asymptote. Okay? Alright. Now, because we were given a restricted domain of minus 3 to 3, we're going to substitute minus 3 into our equation, and we're also going to substitute x equals 3. Okay? So, let's do that. When x is equal to minus 3, y is equal to 1 over minus 3 minus 2, which is minus a fifth. Okay, so the curve stops at minus 3 minus a fifth. That's one endpoint. Okay, endpoint. And when x is equal to 3, y is equal to 1 over 3 minus 2, which is equal to 1. Okay, so 3, 1 is another endpoint. Okay, and now we're going to put all these things on the, we're going to draw this graph. Okay, so we draw an xy plane. We're going to put in our vertical asymptote, which is x equals 2. Okay. Our horizontal asymptote was the x-axis. So just put dot, dot, dot. You can even put the dots underneath if you like, just to remind yourself that whole thing is the horizontal asymptote. And then we're going to plot our y-intercept, which was 0 minus a half. So we're just going to put minus a half there. All right. And we're going to plot our endpoints as well. So one endpoint was minus 3 minus a fifth. So just put a dot there and state what it is. Okay, label your coordinates. And then the other one was 3, 1. So 3, 1. Label that one as well. All right. And the asymptotes are these two. So you can see that your curve is going to go, okay, it's going to approach both asymptotes and go through those points. Now, you can't make your curve go past this point because that's the end of the domain. So just draw a nice smooth curve. All right, don't put an arrowhead on that one, all right, because you're a restricted domain. And this one, the same thing. It's really going to go like this, but we're going to start here and let it approach this asymptote here. All right. And that completes the graph. But it did say in the question to state the maximum value and the minimum value. Now, the maximum value, okay, as you can see, the curve keeps going up and up and up. It's never going to end. All right. So it's approaching. The maximum value will be infinity. And if you look at this part of the curve, it's going to go down to minus infinity. So the maximum value is infinity and the minimum value is minus infinity.